still entertained. So, it's great to be here. And I will start actually with a story. I was very fortunate a couple of years ago to travel with my wife to Australia, which was a long trip. We were, I mean, always, we were very excited to go there, but also to travel about, in total, 24 hours is very tiresome. So we had not a direct flight, it's still very rare that you can fly there directly. So we had a stopover. So it was 6 hours, stopover somewhere. Okay, we were a little bit nervous about the long flight afterwards. At some point we had to enter the next aircraft. We entered the aircraft, we were sitting there, and then the pilot said, wow, we encountered a problem. We have some fuel leak, so now we have to de-embark, and you have to wait for the next flight. And that was, of course, not a nice travel experience, and we were a little bit agitated. We got relaxed at the point where we had the entrance to the VIP bar, where we had free drinks. At this point, we relaxed and then could fly again. But as an experience and all for the customers, and also as a cost for the airline, because aircraft on ground is not making money, only flying aircrafts are making money. It was not a good thing. So imagine that instead, the airline who knew beforehand that some problem occurred during previous flights, which was small at that point, which later led to some kind of bigger problem, which was discovered. I mean, the big problems get discovered. Airlines, the safety of the passengers is always in the forefront. So all the procedures, of course, worked. We were safe. We just had to wait and embark on the next flight. So when something breaks, usually everything works well. But it would be much nicer to find the problems which start small before something big happens. So, and this is somehow the whole idea of this talk, how to get there. And of course, to get there, we need the data. We are in a data science conference. And now we are entering a new age in airline operations and also in airline manufacturing of aircrafts. Since we first have a new connected, I would say, cloud platform, we can collect data from our aircraft during production, during operation, the in-service data, we have industrial data from manufacturing, and we have also data from supply chain and data from our different subcontractors who provide us part of the solutions. So we have this big data lake called Skywise, and there we can create new solutions for our customers. But what kind of data do we have? Actually, and we can see here, I think it's a single aisle, so we have a small aircraft. This kind of aircraft has 24,000 sensors on board. And if we are going to wide-body aircraft, we have more, triple number of sensors and even more. And most data looks like this, which looks a little bit boring. These are time series. So we have sensor readings in time, and it's not so as sexy as pictures, videos, and so on. It's just readings from sensors. But it's the most data you have in any industrial company. And this data is very valuable. This is comparable to a heartbeat. If you go to a doctor and the doctor looks at your heart, you also have time series from your electrocardiogram. And there you can discover if you are healthy or not. And exactly this is what we want to do with our aircraft and also different assets. We want to discover if they're healthy or not and do it very early. So this is a very valuable data for us. But it's a very complex problem. So we heard earlier that you can attack the low-hanging fruits with simple models and create business value fast. In a lot of projects, it's true. It's not so true in this kind of situation. Sorry. Yeah. Here. Hope this is not bringing too much. So, because we have an open dynamical system, if we just look at an engine, what happens there is that we have parameters which describe this engine. We have kind of temperatures, pressures. We have values whether some valve is open or closed. But these values depend not only on it itself, it depends only on what the pilot is doing somewhere in the cockpit. If the pilot is changing something, this value will change. But this change is not described by the system itself, it's described by something else outside. Also, if the weather condition changes, when the pressure outside of the aircraft changes, also some changes will occur. And then, from point to point in time, these outside changes come into the system. There are, of course, physical laws, how temperature will change and pressure will change. So it's a deterministical system with some noise, and this value is changed over time. This system will give an output to some other system. For example, we take hot air from the engines in order to get it into our air conditioning systems and so on. So the demand of the systems outside will go back to the engine and change the parameters. So it's interconnected, open dynamical system, which is very hard to describe. On the right-hand side, you can see one possible, I mean, just selected 3 parameters out of maybe 500 describing one subsystem and plotted how it looks like. So each dot represents one particular temperature, one particular pressure, and one particular some other parameter at one point in time. And if you would see it as a movie, this dot would create this convoluted trace. And also we see 2 colors there. And we see that this the blue and the yellow, and the colors symbolize something, which will come shortly too. So this color symbolizes maybe a situation which is not what we expected, a behavior which we were not expecting. But it looks very similar to the other one. So if you do a simple approach, just go into some space like this and try to separate it by a plane, it will be impossible. So simple models will fail here because it's completely convoluted. It's not clear from the beginning that this yellow points are different from the blue ones, some sense. And that's what we are telling. So anomalies are deviations from expected behavior. And we are not looking for severe anomalies, which are like some value shoots above a temperature which was designed for, because everything like this is already detected. Our aircraft detects these problems, and these problems are detected during maintenance. These problems are reported to the pilots and so on. We are looking for something which is not reported to a pilot, a behavior within the boundaries, but which is still anomalous, which is still not expected. So do I have some kind of pointer here? Let's see. I'm not sure. Okay, on the left-hand side, so we are focused on this red curve, which is a little bit wiggling. And on the left-hand side, you see a regular behavior of this curve. On the right-hand side, you see the same curve, which looks, this red line looks very similar. It's also start to oscillate. But the regions which are highlighted in red are actually anomalies. This region should not be there. And if you just look at this line itself, you will never discover this. You will never understand that this behavior is somehow different. You have to look in the, for example, in the other lines and in the boxes which are highlighted in orange. Because this describe what the pilot has done. These are Boolean values, so yes, 1 or 0 is describing some kind of switching behavior of some valve. And we see that in the first box there is a switching from 0 to 1, and at this point the line starts to oscillate. And this is an expected behavior because in the dynamical systems we are talking about, there is an oscillation which can happen after the switching. While in the other boxes, there were no switching at all, but our parameter starts to oscillate, which is unexpected, or the oscillation starts later after the switching. So this is a context-dependent deviation, and the amplitude of this oscillation is still within the boundaries we have defined previously. So nobody would discover it, because that's not a problem. It can happen. But if you imagine this is a valve which is opens and closes, and this happens very often during the flight. It is not endangering anybody, but it's just happens a lot of time. It's open and closes, open and closes. Then the lifetime of this component drops. And instead of being working there for 10 or 20 years, it just works, I don't know, a couple of months and fails then. And this is what we want to discover and we want to prevent. And of course, the ideal solution is a kind of product we want to provide to our engineers. And we have a lot of engineers who know exactly what they are looking for. They just are, it's impossible to look at 24,000 sensors after each flight for a enormous fleet of aircrafts. So first of all, we are trying to reach human level. We are not going beyond the human to superhuman performance like in other applications. It's enough of us if our system can predict the anomalies and discover them as good as our best engineer. We want to do it automatically and we want to scale. We don't want to do it just for one subsystem. If we achieve it, it will be great, but the best solution would be a scalable solution. And we want to have some kind of semi-automated system where the engineering can come up with data sources, with data which is maybe unlabeled. Usually this data is unlabeled because nobody had looked at these anomalies. So we just know most it's normal, sometimes it's not normal, so unlabeled problem.
And we want to train the best model, maybe automatically in AutoML scope, deploy this model in a platform, and then train continuously. And also provide a feedback mechanism, kind of front end for the engineers to see the problems if they are there, and to label them whether it's true or not, and learn from this experience. And also to monitor the performance of the whole thing. So this is our vision, our dream, and now we have to take the steps towards it. So what are the technical? So now I'm going a little bit more technical details. So what are the approaches towards anomaly detection in time series, so in general? First of all, we have the statistical approaches. There you can see on the left-hand side, like regular and anomalous samples, and you see we have a time series. And we just can take each point in time and put it into a vector. So this is one component of a vector. So if we have 6 million points, for example, 6 million seconds or whatever, or even we have milliseconds readings, then we have a 6 million vector in 6 million dimensional space. It cannot be handled, and also that it's the time aspect is got lost. So what is usually done in the next stage, you reduce the dimension of your space by choosing a very particular basis of the space, which makes the problem clear. The approaches are, for example, wavelets. In the real time, some kind of wiggly, in the time, you see the kind of oscillation which die out. You have functional principal component analysis, and so on. So in the end, you have reduced your 6 million dimensional space to maybe 100 dimensional space, and you have cut it off. You just take the principal components, the most important ones, cut off everything else, and try to see, do you see a difference between normal and not normal behavior in this space? This is shown on the right-hand side. So you see a projection in the 3 principal components from functional principal component analysis. You see in green regular points, and in violet, red, and yellow non-nominal points. And some distinction can be made, and for some problems you can solve it. In the context-dependent approach, and if the problem you look at is not depending on the time series itself, but on the interaction between this time series and some other time series, what the pilot has done in this point in time, what some other value was there. The problem is more complex, because you don't have a vector in one space, you have a set of vectors, and you have to think about it, how you do it. Do you concatenate them? What do you do with them? So that's why the deep learning comes into play. The deep learning approaches, there are 2, more or less predictive and reconstructive, and there you can think of that you try to train a model to learn what does it mean to be healthy, actually. So in if example of the heart, you would try to understand under different conditions, what does it mean to be a healthy person with a healthy heart? How is a healthy heart beating? So in the case of airplanes, you would gather all the parameters of your subsystem. From the flights, you knew there were no problems, probably. So luckily, in most cases, there are no. So we have a huge data set of normal flights. And then you train the model on these nominal conditions. In the first case, in the predictive case, you try, the model has the task to predict the next value at some point in time from the previous values. So you do a predictive model, you actually predict the future from the past, from all the values you have, and since the model is trained on nominal data, it will predict nominal behavior of your parameter. In the reconstructive approach, you put your data in some kind of autoencoder, and this approach is a little bit similar to the statistical one, because you also have a latent dimension in between, a reduced representation of your time series, but here the basis is chosen by the model itself and not by you. And then you try to reconstruct it back. And since you also train on nominal data, this latent representation captures the nominal behavior. In both cases, after the prediction or reconstruction, you know how your system would have behaved under nominal conditions. And then you compare it with the actual measured data. And you see it in the middle in blue and red. In blue, the measured data, in red, the predictions. You see there are differences, and you try to quantify the differences, because this is an indication of an anomaly. So you compute the residuals, the differences, and then you try to find a cutoff where, at which stage you say, okay, this is severe enough, this is an anomaly. And so you have really an anomaly in time frame telling you, okay, from this point in time to this one, this parameter behaved some kind of crazy. So you can use long short-term memory networks, you can use CNNs, autoencoders, GANs, whatever you like, but I mean, the algorithms are out there. The trick is then to find a model which actually predicts something interesting or works. So first of all, we have a foundation in our site. Our team in our research department had created a library for combining different approaches. It's called Advised. It has the statistical approaches in it. It has the reconstructive approaches within it. Currently, it is used across Airbus Defense and Space, Airbus helicopters, Airbus Commercial, where I'm from. And at some point, we are now currently thinking about maybe open sourcing this library to the open world to provide this knowledge to many companies who are struggling with this problem in different industries, so we can all learn from it and participate together in this kind of development. There is a lot of open source development in terms of image recognition, natural language processing, but there is not so much effort in this kind of industrial setting. And we are very interested into it. Okay. So we have a foundation with this library, but we are building on top of it a model. So one model we are looking at is a predictor model using two-layer LSTM, long short-term memory network. This model is based originally on a paper from NASA from 2018, KDD. And we have started working on it and improving it and using it as a kind of our baseline. So we ingest from the past readings of up to hundreds of sensors at different points in time, feed into our system and try to predict a point in the future, how this one parameter we're interested in will behave in the future. And there are a lot of choices to be made. First of all, you can decide whether you ingest actually all the values you have, all the maybe 500 sensors, and try to predict one. Or do you ingest the sensor itself and try to build a completely autoregressive model, how it's sometimes done in time series analysis. You can choose the length of past values to ingest, how long further back in time do you go to predict the future. And you can also decide to predict only the next value. So if you do I don't know, a course online on time series analysis, you will tell you, okay, just build some kind of neural network and predict the next time step. And we will see what happens if you try to do this from this course. And then you can also decide maybe to leave a gap, to tell the model, okay, don't predict me the next time step, predict me the behavior of this variable in 30 seconds. And not only 1 point, but maybe 10 points. And each of these choices will change the behavior of the model. So these are a little bit complicated plots here. So on the upper half, you see always time on the x-axis and some normalized value of a variable on the y-axis going between minus 0.6 and 0.6. And in blue is always the actual measured value, and in red the prediction. And on the downhand, on the lower side, you see always the correlation between this prediction and measured values on the y-axis and the shift on the x-axis. So we shift them in time and see if they are correlated or not, how strongly. And first of all, we do a completely autoregressive model. We only take the value we want to predict in the past to predict the future, and we do it like an online course, predicting one step ahead. And what we get is actually we cannot see the difference between our prediction and the model, because the model has learned to take the value it had before in order to predict the next one. So it's completely correlated, autocorrelated model at 1 second. So if there are anomalies in your plot, you will predict the anomalies, and you will learn nothing at all. Okay, the next step you can do is take this autoregressive model, but tell it to predict not the next value, but the value maybe 30 seconds ahead. And we see already that this choice has dampened the oscillations in the predictions. So the predictions are now different from the actual values, and also the correlation changes from 1 to 0.94 at some intermediate time. So this model already, depending on the cutoff, would predict some anomalies. It would start to predict them, because there is a difference. And now if you go fully multivariate and predict, here we plotted, inserted 90 variables simultaneously to predict the one in the future, then you see the behavior changes drastically. So we have no more oscillations, we have stable conditions at some points, the correlation plot changes, and this is at this point we start to have a working model for our problem. Still, there is the question how to choose the cutoff, which is also a very critical question. And each paper you read has a different definition how to do it, so this is still an ongoing research question. And so how do we do this product at Airbus? So first of all, we are working very close together with engineers who have the knowledge of the data. If you just a data science team, in some other situations we know, in some other companies there are a data science team, because the engineers are very busy, they have always things to do, so they have not much time. So you need their time. So if you're not working together with them, you will fail. So we try to encourage them, and they're very interested in this project and work with us together. And first of all, we try to have an understanding of one subsystem, part of an engine, something like this. Create something which is valuable and see whether it can be scaled or not. If we succeed already in this stage and it's valuable, then even if we fail in the later stages, we have a product which can be used very fast. Then we try to scale up to the whole system, maybe going to engine, going to the whole aircraft, and so on. And then we want maybe to transfer it to other assets producing time series, for manufacturing machines or something like that. And then it starts from the beginning. But as I said already with the library, it's not only about us, data science team at Airbus and Airbus itself. We are open to co-innovation. We want to work together. We want to find out what is the best models out there. What are the other companies doing? What are the best approaches to it? Maybe somebody else has already solved it. So that's why we have also started a challenge on it. We have our own platform called AI Gym. And this is a platform for data science challenges, similar to Kaggle, but you will win no money, actually. So sorry about it. You will be invited to Toulouse to a nice gathering like this one. But of course, we will enter at some point maybe negotiations with the winner and maybe some other companies. We are interested in collaboration. We are interested in working together. And also, as a side effect of this challenge, you get access to data which is usually not available out there. We had challenges on NLP, because NLP at Airbus is also something different, because we have documents written in 3 languages simultaneously with a number of acronyms which nobody else uses, so all the approaches you just download from Google will not work. But in our case, we had also a challenge on time series. Here. We have anonymized data, so it cannot be traced back to anything. You don't know what parameters are. They're called parameter 1 to parameter 49, or whatever, to 89. So we have 89 parameters, completely unlabeled data, and we have 1,000 files. So it's a huge data set. In these files, we have flights and ground tests. And we told the participants that, OK, treat this data as normal, and we advise you to look for anomalies in following 8 parameters. Let's see if you succeed or not. First of all, they managed to find 17 anomalies in this huge training set. And then we said, OK, try to find your best model, and we applied to a validation set. And this set contained 50 files, ground tests and flights. And in this data set, together with engineering, we tried to create labels. And this is very demanding work. We can see here on the picture my colleague Sarah sitting with one of the engineers, Torsten. And there is a box on the table because another engineer in Toulouse is also on the phone. And for 50 flights and for only 8 sensors describing small part of one subsystem, it costed already 50 man-hours in order to create these anomalies. So you see in the plot the submissions from participants in the shaded regions and the true anomalies in the boxes, in orange boxes. So we created also front end where the engineers were able to see. This front end was developed in a way that it looks exactly like their legacy system from engineering, but in a modern environment. And you can also see the anomalies, but also label them. You can create bounding boxes, and we're storing it. So we labeled in total 79 anomalies in this huge task. And this is a very big asset, because we are thinking about also releasing actually this data set to the public, with this thousands of training data and this really golden data set of really labeled anomalies in order to increase and to encourage research in this area. So, and the challenge is unlabeled, so it's semi-supervised, the only information you have on normality of the data. And the baseline is that you fail, because you cannot label the whole flight anomalous or not. We really wanted to have from which point, in which sensor, from which point in time to which there were an anomaly. And we computed the overlaps. We counted only, each anomaly is counted only once. So you cannot provide a longer one to hit different others and so on. So the baseline is actually 0. So you will find nothing or you will fail. And we see that the winner team reached a precision and recall of approximately 0.5, which is very good considering the setting. So we were very happy about it. So, and we are now working with this company, Dataset from Switzerland, on the next stages of our product. And we hope that we, of course, in the first stage can improve vastly, having more engineering knowledge putting into it, improve vastly over this result and go further on. And so we are coming to the conclusion. We are trying to build an industrial anomaly detection service, first for one subsystem, using mature infrastructure from the beginning. So we want either we fail horribly already in this part, or if we succeed, we had a product which is used by engineers after 6 months maybe in their daily work. We have to, and this should be good enough so that they really trust the predictions and look at the data, which costs a lot of time. We want to have, we work very closely together with them to have their input at each stage, to understand their demands and what the value is. And we employ probably, what is state of the art out there in terms of AI models or deep learning models for time series prediction, anomaly detection, and so on. So thank you very much, and I'm open for questions.